that we were talking about demodulators for binary digital modulation schemes, and we have looked at both coherent as well as non-coherent demodulators, and what we have just in summary, antipodal schemes like BPSK require coherent receivers. Orthogonal binary schemes like on-off keying or frequency shift keying, we can use either coherent or non-coherent receivers, right? What we like now to do is to gain some insight about how these receivers actually perform. These are the best known receivers in Gaussian noise, right? These are the optimum receivers in Gaussian noise, the optimum coherent receivers and the optimum non-coherent receivers. The question now is how do they perform? We like to be able to predict, that is, be able to say what will be the error rate that will come out of a digital receiver or particular binary modulation scheme for the corresponding optimum receiver for a given signal to noise ratio that may be available at its input, right? So we like to do some analysis of performance before we proceed further with the demodulation of more general digital modulation schemes like Emery schemes, okay? And then after we have developed this insight, we will go over to the Emery schemes. So the title for today's talk will be essentially, that is, analysis. Is that visible? No, I think it's a bit faint. Of binary digital modulation schemes. All right. Now, to do this analysis, ultimately what we want to do is be able to predict the error rate or the probability of error, that is the probability of mistaking a transmitted 0 for a received 1 or vice versa, right? The probability of error as a function of the two most important parameters that we will have to deal with all the time, namely the signal and the noise, right? Actually the single parameter signal to noise ratio, as you may seem fit to define it. Now, before we can do that, we have to be therefore able to express the statistical properties of the output of the match filter, because ultimately, if you remember, the decision statistic is the output that we sample and then pass through a threshold, right, on the basis of which we decide whether or not a 0 or 1 has been transmitted. So the most important parameter whose properties we must investigate is that decision statistic, that is that sample value which is being compared with a threshold for a decision. Depending on how that behaves, what are its statistical properties, what kind of probability distribution function does it have, right, we will be able to do this prediction that we want to do. So we must therefore be able to appreciate the nature of the decision statistic, let me denote it by X, for each of the cases that we are dealing with, namely for coherent receivers on the one hand and this is your decision statistic. And also for non-coherent receivers on the other hand. So that's what we must do first to be able to proceed further with the analysis, right, where X is the sample output which you are comparing with the threshold for taking the final decision regarding what was transmitted or what has been received. Okay. Now for the case of coherent receivers, consider the case of coherent receivers first. What is X in that case? X is nothing but the match filter output, right? And we already know the properties of the match filter output, both when a signal is presented to it as well as when a noise is presented to it, right? We have seen that, we have studied that adequately. When a signal is presented to it, which is to which the signal to which the filter is matched, the output at the sampling instant is at the peak value. Suppose the signal is AST. We have seen that the output will be A, assuming of course that ST is normalized appropriately with unit energy situation. On the other hand, when noise is presented to it, white Gaussian noise with a power spectral density function of n0 by 2, we have seen that the output at the sampling instant, or for that matter at any instant, is a random variable with a variance equal to n0 by 2, right? We have seen that. So therefore, for the case of coherent receivers, we have a fairly good understanding, in fact a perfect understanding of what the output statistics are. It stems from the following, these observations that we just made. The first observation is, if the input is a Gaussian noise process to a filter, the output we know will be a Gaussian noise process whose variance we know, right? If it is presented with noise alone, it will be a Gaussian noise process with this variance and 0 mean, because the input is 0 mean. On the other hand, if it is coming along with some signal, either AST or minus AST or whatever, the output process will now be again a white output will again be a Gaussian noise process with the same variance, but its mean will be appropriately shifted, right? It will be either A or whatever this A or minus A, depending on if you are considering, let's say, antipodal schemes, right? So in the case of coherent receivers, we fairly well understand the statistics of this decision statistic X with which we will have to work, which is compared with the threshold, and therefore we will be able to do the analysis very easily, as we will see very soon, right? Because we know it is Gaussian, we know its variance, we know its mean, we can write down the expression for its probability density function at the output, right? Because all the parameters that we need to know are known to us. However, the same cannot be said about non-coherent receivers. Well, it can be said, but we will have to do a bit of analysis of that, and therefore what I will do first is, just like we have a reasonably good understanding of the statistics of X in the case of coherent receivers, we like to also have a similar understanding of the statistics of X for the case of non-coherent receivers before I proceed with the analysis, because I want to do both the analysis very one after another. So let's start with a discussion of the noise properties at the output of non-coherent receivers. Okay. What are we doing in the case of a non-coherent receiver? Basically, if you recollect what we discussed last time, the input signal is being brought down to the baseband form. If you take that form, that's the most convenient form to analyze, and then each of the I and Q outputs are being squared and summed, and then we take the square root of this, right? As far as the two outputs I and Q are concerned, they are match filter outputs whose properties we understand in the same way that we just discussed, right? Each of them will behave exactly in the same way. It will have some mean, some variance, right? We will have to identify what is the mean and what is the variance. Let's, in fact, to start with, assume that only noise is present. So the mean at the output of the match filters in I and Q both channels will be 0, and the variance will also be identical, equal to sigma square. And we also know that because they are quadrature channels, the corresponding noises will be uncorrelated, right. So we will start with this understanding of the I and Q outputs, and finally our decision statistic is really going to be in terms of this I square plus Q square square root of that. So what we like to understand is how does this quantity behave statistically, okay. That is the basic, because this is what we are finally going to sample and compare with the threshold for making a decision, or compare with another similar quantity for making a decision, right. In the case of orthogonal signaling schemes, we will be doing this computation for both the signals separately and then comparing the two together. For example, in FSK, right, for each of the two signals that you might be transmitting, you will do this computation and then mutually they will be compared. Whichever is larger, we will take the decision in favor of that. Fine. So basically this is a problem at hand, and let us to start with consider the noise alone case, and then we will add signal to it later. So as I said, I is Gaussian individually, so is Q, right, that we already discussed a number of times now, and they are uncorrelated, which in this case would also imply that they are statistically independent, because we are assuming they are Gaussian, right, because the input is a Gaussian process, they are Gaussian. Therefore, really speaking, if I will not use the notation I and Q for the time being, I will just go back to X and Y. The outputs of the two quadrature channels, I am denoting now these outputs by the random variables X and Y, right. We can think of these two random variables having a joint probability density function, which is essentially a very simple kind of two-dimensional Gaussian density function, and since they are independent, this two-dimensional Gaussian density function is obtained by simply multiplying the individual Gaussian density functions, right. So it will be 1 by 2 pi sigma, each of them has the same variance, both of them have same variance, e to the power minus x square plus y square upon 2 sigma square, okay. And what is our interest? Our interest is in, let me define a random variable R, which is obtained from these two random variables X and Y in this manner. We like to understand what are the properties of R. Do you know what the answer is? If you know the answer, then we can skip this analysis. Is that okay with everybody? We can skip it, or does everybody know that R will be a Rayleigh random variable?
Yes.
So I can skip it? We know it and still don't skip it?
So we know this, but we are not derived.
You don't know how to do it?
No.
Alright, let's go through it. It's very simple. Let me define R in this manner. Let me also define another random variable phi, which is tan inverse arctangent of y upon x, okay. So essentially what I am saying is, we are going to do a coordinate transformation to represent the same x y values by a corresponding set of R phi values, right. We just done a rectangular to polar coordinate transformation of these two random variables. The same point in the two-dimensional space is now being represented in terms of its polar coordinates R and phi, right. And the basic idea of doing this kind of studying these kinds of transformations for their statistical properties is to consider the probabilities, consider the probability of occurrence of an event which lies in an elemental area in the same space, both in terms of this density function as well as in terms of the density function of the transformed variables R and phi, okay. Incidentally, this density function is something like this. I mean, you have a Gaussian density function in 2 dimension. This is your x, this is your y dimension, and you have some kind of a inverted pyramid. It's a kind of pyramid actually, except that it's more like a tent. And so if you're somewhere on this plane, xy plane, you can as well represent it by r and phi, and the relationship between the 2 density functions, the 2 joint density functions in terms of xy as well as r phi is obtained by equating the probabilities of occurrence of corresponding to an elemental area in this xy plane. So if you do that, if we consider an elementary area, let's say A, and consider the probability that r and phi will lie in this elemental area, right? It will be this, okay, where A is a small elementary area with r and phi as the center. Similarly, we can also compute the same probability by considering the corresponding pxy, right? Basically, this is the starting point of most of these kinds of analysis from fundamentals. Now, let's substitute for pxy, that is 1 by 2 pi sigma square e to the power minus x square plus y square upon 2 sigma square dx dy, right? And now let me make the substitutions that we just discussed, that is r equal to this and phi equal to this. If we do that, we can write this as before, so let me just rewrite it for you for completeness sake here. R is this, phi is this, and we'll also have to do something about dr d phi. Dr d phi is, in fact, r dr d phi is equal to dx dy, right? So making the substitutions, we'll get one by 2 pi sigma square. This will become r square by 2 sigma square, right? And this dx dy will be replaced with r dr d phi. Okay. Now, if you compare the two integrals, it's obvious that p r phi, the joint density function of r and phi, is nothing but this quantity, right? Because we got it in the same form, right? So both the integrals are now with respect to r and phi. So we can write an expression for p r phi as 1 by 2 pi sigma square e to the power minus r square by 2 sigma square, sorry, into r also. This r also has to come here. Fine. Just look at this again. This r into this. All right. But what is our interest? We are not really interested in phi at all, because finally we are only looking at r. So we want to obtain the density function of r from this joint density function of r and phi. How do we do that? Integrate out the other random variable in which we are not interested. If you do that, simply carry out an integration of this over phi. In fact, it is not a function of phi at all, right? It's a constant with respect to phi. Essentially, it will be from 0 to 2 pi into d phi, integral of this into d phi, and that will essentially become, this 2 pi will disappear, right? So you'll be left with p r as r by sigma square e to the power minus r square by 2 sigma square. Of course, it's understood that r is going to be greater than or equal to 0 because of the way it is being defined. This is precisely what is known as the Rayleigh density function. Rayleigh PDF. Okay. So now you know how it is derived. It's really very simple. So what we have learnt is that when we pass or when we take the envelope of a Gaussian random process, that envelope will have a density function which is Rayleigh. That's essentially what it boils down to. If you were interested in phi, you could also obtain the density function of phi by integrating over R. It will turn out that phi will be a uniform distributed random variable between 0 to 2 pi, right, with a density function of 1 by 2 pi between that. But we are not interested in that, so I will leave it at that. Just a few very important properties, very basic properties of this Rayleigh density function. This is no longer a zero mean random variable. It's obvious, isn't it? Because the density function is defined only for positive values of R, right? In fact, this is how it looks like. It's not symmetric. Gaussian was symmetric. It's no longer symmetric, and obviously it is not zero mean. In fact, it can be very easily checked, and I'd like you to do that yourself, that the mean of this is sigma times root of pi by 2. The input process was zero mean Gaussian, input noise was zero mean Gaussian. The output is a Rayleigh random variable whose mean is not 0, right? It's this value, depends on the variance. Similarly, its variance is smaller than the input variance, is given by 2 minus pi by 2 sigma square. This is something you can verify yourself easily. Just like we have a standardized form for the Gaussian density function, you are familiar with that standard form for the Gaussian density function, in which the mean is taken to be 0 and the variance is taken to be 1. We similarly have a standardized form or a standard form for the Rayleigh density function, in which sigma square is taken as unity. And I will just therefore, for the sake of completeness, write it for you. The standard Rayleigh density function PRA, let's say in terms of some random variable z, is defined as z e to the power minus z square by 2, right? Just same expression except that you have put sigma square equal to 1 for z greater than or equal to 0. So in terms of this standard density function, standard Rayleigh density function, PR as we have just derived can be obtained by putting z equal to r by sigma, right? So essentially we can say that your PR is, if you make the substitution, 1 by sigma PRA r by sigma. Okay, all I am saying is this PR can be obtained from Z by replacing r by sigma, and then of course you will have to scale it up with 1 by sigma to get the same expression. Okay. So in terms of the standardized Rayleigh distribution function, the non-standardized distribution with a non-unity sigma is written like this. That's all. Now that was the case when the input to this system, this envelope match filter envelope detector combination, was only noise. Now that is all right for situations like we are only interested to know what is the output noise properties, but our interest is to know both how it will behave with noise as well as when it is coming with signal as well as noise, right? So now let's consider the case of signal plus noise. same system, but the input is signal as well as noise. Now, what will be the essential difference at the IQ level, at the XY level? Mean will not be not 0, right? When the signal is there, at the IQ level, at the two quadrature mesh filters level, again we'll have Gaussian random variables, but there will be non-zero mean Gaussian random variables. Let's say, therefore let me write it down. Mean is no longer 0. At the IQ outputs.
Excuse me.
Yes, please.
So how can we say that both I and Q things will be Gaussian variables? Because the signal as well as the noise, and we know the noise to be a Gaussian process.
Sure.
But signal, nowhere we said that it's a Gaussian.
Signal, we know what effect the signal has. We already discussed at the beginning of today's lecture also. The signal, the presence of signal with noise will essentially change the mean of the, because the signal is a deterministic signal. It's not random at all. And after match filtering, suppose signal alone was present, at the sampling instant we get a value A.
Yeah.
With noise, we get that value A with noise fluctuations, right? So the mean value is A with some variance depending on the noise input. So it remains Gaussian, only its mean is different in the presence of signal, because it's a linear processor, right? Match filter is a linear filter. So since the input is essentially non-zero mean Gaussian noise in the presence of signal, it's a input, mind you, is a time has a mean which is time varying. It depends on signal ST. So does output. Its mean is time varying. But we are only interested in the output random variable that results from sampling the output at t equal to capital T.
Okay.
That has a very definite value.
That is it.
That has a very definite value equal to A, no matter what is the shape of the signal, right? So the output process at the output of the match filter is a Gaussian process in general with a time varying mean, right? Because output has a definite waveform, right? So the mean is really time varying, but at the sampling instant at which we are interested, that value is known to us, and we are really looking at that value, right? So the essential difference in this case to start with is that at the IQ level, at IQ outputs, we have Gaussian random variables with non-zero mean. Okay, this is our starting point. So therefore, let's consider the general problem of combining two Gaussian random variables x and y, such that x has a mean x bar and y has a mean y bar. So this is the mean values, let's say, assume, let the means be this, and we are now interested in finding out what are the properties of square root of I square plus q square when I and q are non-zero mean random Gaussian random variables. That is the question.
So the mean of the both the I and Q channel shape or one
I am considering a general case. In fact, they will be, in general they will be different in the quadrature channel. Can you justify why? His question was, would these means be same or different? That was the question, Vivek.
So mean will change both I and channel Q while only one of the channels. Earlier it was 0. Now
Okay.
it will be A.
Let's recollect the case of on off key, the simplest case, right? If you remember, the output was represented by AK cosine theta k plus JA k sine theta, where theta is your unknown phase. So the mean in one case, in one channel is AK cosine theta, in the other channel it is AK sine theta, right? So in general, they can be different depending on what is the value of the unknown phase, right? Of course, if theta is eliminated beforehand by doing a phase recovery and phase compensation, then they can be identical also, right? So in general, they can be different or same. So, let us represent these means also in terms of polar coordinates. We have some arbitrary means x bar y bar. We can also represent them in terms of, let us say, some values a cosine theta and a sin theta with an appropriate pair of a and theta values. Fine. Because we are going to go from rectangular coordinates to polar coordinates, let us represent these mean values also in terms of polar coordinates. Right. The rest is everything, the rest is absolutely same. So, theta here is some unknown phase angle, and we start with let us say p I x, that will be 1 by root 2 pi sigma e to the power. What will be the difference? We will now have x minus a cosine theta whole square by 2 sigma square. Similarly, pqx, pqy, let me call it, will be 1 by root 2 pi sigma okay, and they will also be uncorrelated. So, we can write down the density function, joint density function of these two as a product of these two, and proceed in absolutely the same way as we did for the noise alone case, right, and do some simplification. If we do that, I will skip those identical steps, they are absolutely identical, there is no difference, just a little bit of trigonometric manipulation which you can do yourself. You will find that you can write down the expression for the joint density function of r and phi, where r and phi are defined in the same way as before, that is r is square root of x square plus y square and phi is tan inverse y by x. Will be, this density function will be r upon 2 pi sigma square e to the power minus r square minus 2 a r into cosine theta minus phi plus a square, this whole thing, this whole exponent divided by 2 sigma square. Okay, I am sure you will be able to verify that very easily. But do you understand the result? Of course, one can obtain the density function of r and phi individually by integrating out the other variable, which is what we will do now. But up to this step is straightforward substitution and a little bit of trigonometric manipulation, not much. So, ultimately, since phi is not of much interest to us in our application, we will integrate out phi and see what happens to PR. You can write this as r by 2 pi sigma square. Since I am integrating over phi, all these are constants, I can take it outside the integral, minus r square plus a square upon 2 sigma square into integral from 0 to 2 pi of e to the power, this minus and minus will become plus, this 2 and 2 will cancel, right. So, you can write a r cosine theta minus phi upon sigma square. We are integrating over phi. Phi. Actually, you could have written phi minus theta instead of theta minus phi because cosine is even function. Now, this we can write as r by sigma square into e to the power minus r square plus a square upon 2 sigma square into, now this particular integral is a standard integral, which is nothing but the so called modified Bessel function of the first kind and 0 order. is denoted by I sub 0 with this as the parameter. Let me define what is I0 formally. The function I sub 0 x, the so called modified Bessel function of first kind and 0th order. Is formally defined as follows. I sub 0 x is 1 by 2 pi 0 to 2 pi e to the power x cosine phi d phi. So this is a formal definition. You can apply the definition and see that this is what you will get here. What is the difference between this integral and what we have defined here? There is a theta there. This phi here can be brought to this side. This can be made phi minus theta rather than theta minus phi, so that doesn't make any difference. But actually it is also independent of theta. This same thing I can put a phi minus theta and go from 0 to pi, because it's actually a periodic function. It doesn't really matter in phase offset, because ultimately you are going to consider the whole period or 2 pi. So it turns out to be independent of theta, this integral, right? So this is our final result, this one. Okay. So as you can see, this density function depends on, yes please.
How is it independent of theta? They shift
this definition, if I put a phi minus theta here, it doesn't affect the value of theta in the integral. It's a periodic function, right? Isn't it? Because phi minus theta, no matter what the value of theta is, when you consider cosine phi minus theta, it will go over one full period, right? Because of this cosine factor, it doesn't depend on theta. Yes, as you can see, this density function depends on A, which was, remember how A was defined? A was the output amplitude of the mean value. This is the mean value in terms of amplitude, polar coordinates. Depends on noise variance. Of course, you can see that when A is 0, what happens? It turns out that, okay, this will be 1. I0 x at x equal to 0 will be 1, which is very easy to check, because this will become this will become 1, and this 2 pi and 2 pi will cancel, and that's 1. Fine. So this will reduce to the Rayleigh density function when A is equal to 0, right? So actually speaking, this is the so-called Rician density function, derived from the name of communication theorist by the name of Rice, R-I-C-E. It's called the Rician density function, and it's not really a single density function. It's a whole family of distribution functions, the family being defined by the parameters A and sigma, right? So the standardized form of the Rician density function is as follows. Are you familiar with the Rician density? Okay, now you are. I hope. So again, if we define z equal to r by sigma and lambda as a by sigma, then we define P Rician in terms of the standard variables z and lambda as z e to the power minus z square plus lambda square I 0 lambda z. Okay. So if we normalize r by sigma as well as a by sigma, right, that same density function will reduce to this form. This will reduce to this form, which is known as a standard form of the Rician density function. So as you can see, it's a one parameter family, right? It's parameterized by the parameter lambda. It's a family of PDFs depending on lambda. I am sure you like to look at what this family looks like. I think before that I should also show you what this function looks like, I0x. Do you have any idea what this function is like? It's a monotonically increasing function. It looks like this. Okay, I0x. If you were to plot it as a function of x, this is how the modified. Yes.
Sigma equal to 1. I mean, we are normalizing.
Yes.
With r square plus a square by 2 factor in the exponent.
Yes.
In
All
the
right.
previous expression which you have given,
Yes.
it was e to the power minus r square plus a square by 2 sigma square.
Mm-hmm.
So you put sigma equal to 1, that is r square plus a square by 2. Here we give e to the power minus a square plus sigma.
Okay, let me just check. Is there any mistake anywhere? Yeah, I think probably this is by 2. Yeah. Yeah, I think that 2 has been omitted from me. Any other comment? Then I think I should show you what this family of density functions look like. This is a typical set of plots for the Rician PDF family. As you can see, for lambda equal to 0, we have the same shape I discussed before, namely the Rayleigh, and essentially for different values of lambda, which basically what is lambda, if you remember? A by sigma, and A will depend on the input signal amplitude. A by sigma is some kind of a signal to noise ratio measure, right? So as the signal to noise ratio increases, at the output you will find a density function which shifts to the right and gets flattened out, right? Its tails become longer and longer, right? It extends more and more towards infinity, and in fact you might see a resemblance of this density function with something that is known to you. Looks like a Gaussian density function, right? So asymptotically, as the signal to noise ratio becomes large, the Rician density function essentially is like a Gaussian density function. It's not exactly a Gaussian density function, because a Gaussian density function will never become 0 at any point, whereas it always starts from 0, but it resembles a Gaussian density function more and more. Okay, so with this as a background, we are now ready to do our error rate analysis. Do you have any questions first before we proceed further? So what we have learned so far is how to describe statistically the random variables which we will be working with at the in the case of coherent as well as non-coherent receivers. In the case of coherent receivers, we will always be working with Gaussian random variables, either 0 mean or non-zero mean, right? In the case of non-coherent receivers, when we are considering the case of noise alone, the random variable will be considering the output is Rayleigh. If you are considering it along with signal, it will be one of the density functions belonging to this Rician family. That is the essential point to remember. So obviously, as you can see, coherent receivers are easier to analyze as compared with non-coherent receivers, right? Because non-coherent receivers bring in this additional complication. Yes.
The analysis we've done just now.
Yes.
Is for coherent.
Non-coherent.
It's for.
You tell me.
We've done it for a cos theta, a sin theta. So it describes both.
No, but ultimately, what is this Richian density function? It is R. It's the density function of the random variable R equal to square root of x square plus y square. Where do we do that computation? In non-coherent receivers, right? We don't do that computation for coherent receivers. We don't look at envelope in coherent receivers. We look at envelope only in non-coherent receivers, right? And this is a density function of the envelope, right? An envelope we look at only in non-coherent receivers where phase is not known or cannot be known. Phase cannot be measured, and therefore we want to eliminate phase through this envelope operation, right? Square root of x square plus y square operation. Okay, we are now ready to discuss error rates for binary signaling. Yes, Varun? Okay, let me proceed with the analysis now. We will make a very simple assumption which we have been making even at the time of developing the receivers, discussion of receivers itself. One is, we will assume that the channel is distortionless, so that does not come into the picture. So we are not looking at the effects of any non-idealities of the channel. Second is that the noise is of the so-called additive white Gaussian type. Right? We could also have what is called multiplicative noise, noise which multiplies the input signal. There are models, there are situations where that kind of a model is appropriate. However, most of the commonly used channels will exhibit this kind of noise addition, and this is sometimes also known by the name of AWGN channel, additive white Gaussian noise channel. So we will be making these standard assumptions in this analysis and then proceed on to calculate the error rates. So let us write our received signal Vt as the sum of the transmitted signal, say, let us say Ct plus this noise Nt, and there is no other distortion, right? Ct comes along as such except for the addition of white Gaussian noise at the receiver. So this is your transmitted waveform. This is noise with a power spectral density function of n sub 0 by 2. The model for our demodulator is, in the case of coherent receivers, to start with I will consider coherent receivers because they are easier to deal with. We have a match filter followed by a sampling device. So we will do an operation of sampling at time instance t equal to kt, right, plus this is followed by a comparator or a comparison with a threshold detector. And it is this value, the sample value, which is the decision statistic, which I will denote by x. So x is the decision statistic, which is the sample value, right? Now as we have just tried to appreciate, this decision statistic x will in general have different distributions when a 0 is transmitted and when a 1 is transmitted, right. For example, suppose it was on off keying, right. The match filter output in both cases, this decision statistic in both cases will be Gaussian, but in one case it will be 0 mean, in the other case it will be with a mean of A. So they are both Gaussian, but the detailed distribution is different in each case, right. So in general, the test statistic or the decision statistic will have different distributions for a 0 transmission and for a 1 transmission. Let me denote these two possible distributions as P sub 0x and P sub 1x. Alright, let me just complete this. So this is the PDF of x when 0 is transmitted, and that is the PDF of x when 1 is transmitted. We will start from here next time. अभी तो टाइम था 5 मिनट, जल्दी रोक लिया.